This is a talk by special request to get him back again. Lots of people say there's nothing new in propagation. They're wrong. Chris has been doing some really, really fundamental work, set off by Graham over there. Originally, he's in there, isn't he? And he has been looking at the polarisation of signals via 6 meters via sporadic E. And you think, well, you transmit horizontal, you receive horizontal, don't you? Chris, take it away.
I'm transmitting on 656 point something megahertz, it says on here. Good afternoon. I wasn't expecting a roller disco, as I just like to say that, you know, you're all on wheels. So if I see chairs sliding towards the door, I know that I'm missing the point. I mean, obviously, the slides are being echoed over there, but because I've got to press buttons, I will be over here, just so you know. Yes, so I've been interested in 6 meter propagation for the past years, 35 years. First got on the band in the 80s. Propagation of around polarisation has become an interest in the last 3 or 4 years. It started off as a purely amateur interest. And then I presented here in 2016. And by the way, some of you may have seen that presentation in 2016. And there's a little update in 2017. You will have seen some of this before. But there is quite a lot of new stuff. It then attracted the attention of Catherine Mitchell over there, Professor Catherine Mitchell, I should say, who said, let's help you. And then it sort of turned out that the best way of helping me was for me to register for a PhD, which seems to sort of bring with it a whole load of extra work that I didn't really have in mind. But it has actually been very instructive, and it gives me access to the literature and to software and all sorts of other things, and also the advice of Catherine and her colleagues, 2 of whom are over there from the US. Right, so I'm going to talk about why I'm interested in this, why you should care about polarisation, assuming you're active on 6 meters, or in fact, if you're active on any band, to be perfectly honest. Then I'll sort of take you through the story of what I've been doing over the last 3-ish plus years, and sort of towards the back end, some of it's been published in a conference paper, and that's sort of like the middle bit, if you like. And then there's more, which is perhaps not, well, it's definitely not ready for publication yet, but it's very interesting, I think, anyway. But then that's just me, isn't it? So what? You know, you are all mature, experienced radio amateurs. I can see that from the amount of grey hair. So clearly, you all know what polarisation is, right? So I don't need to tell you about it. But it's historical fact that most people on HF and VHF use horizontal polarisation. And of course, on VHF, you transmit horizontal and it arrives at the other end horizontal too, doesn't it? Actually, it doesn't always. Of course, on HF, you just assume it's been completely scrambled and there's nothing you can do about it. But in the middle, particularly around 6 meters, you can actually start to look at what's really happening in a way that's actually quite difficult at HF, because at HF, God knows what's going on. There's probably 3 or 4 different mechanisms in any particular path. Whereas at 6, you have much more chance of homing in on the right thing. So initially, I was just interested in polarisation, so I looked at things like Aurora, Tropo, but fairly quickly honed in on Sporadic E, because obviously that's the way we mostly communicate on 6 meters anyway. So, agenda, what is it? Why do you care? What does the ionosphere do to it? A bit about the experimental setup. I'm happy to answer questions as we go through or at the end. I don't know if that clock's right. Oh, it is. Okay, so I know roughly how much time I've got as well. And then some of the results that I've found, things that I can be fairly confident of saying and things that I'm not yet confident of saying, and some outstanding questions which raise some interesting possibilities from not only from a scientific point of view, from an amateur radio operating point of view as well. So whether you like it or not, your aerial is transmitting horizontal or vertical. If you're not a mobile, it's almost certainly horizontal. That's historical and practical, because obviously if you've got a metal mast, you know, you don't want the mast to be in the same plane as your antenna. Mobile is a different matter. And cross-polarization, if you're using the opposite polarization, theoretically is infinite. Loss or lack of pickup, reality is more like 10 or 20 dBs, but it's still a real number. So there you go, linear polarization. Wonderful what you can find on Wikipedia. So, you know, the magnetic field creates, the varying magnetic field creates a varying electric field, which creates a varying magnetic field, blah, 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 and off it goes. And it's very much like when you're using your Polaroid sunglasses. You don't need to hear this, you obviously know this already, but the light reflected from the water on the ground or whatever tends to be strongly horizontally polarized because of the different reflectivity of horizontal and vertical polarization at that interface, and your sunglasses are the other way around. They are vertically, they've got a vertical polarization filter effectively built into them. And circular polarization is the other way of doing it. If you think of it as a skipping rope, you know, you can make your skipping rope go up and down, you can make it go side to side. If you're really clever, you can make it go at an angle, or you can make it do that, And that's why you've got multiple potential polarizations of radio waves. And if the X and Y axes, horizontal, vertical, if you like, are 90 degrees out of phase and of equal amplitude, you get circular polarization. Any other combination and you get something that's elliptical or possibly linear. In fact, arguably, circular and linear polarization are special cases of elliptical. So this is what I was fiddling around with Noel earlier. This is what actually, is Graham actually here? G3 TCT? No? Good. He's at every bloody lecture I do, and he always asks the most difficult questions, so I'm glad he's not here. But it was actually his investigations that got me interested in this. What's happened to me sound, Noel? The sound's gone. Oh, there we go. So this is a bit of relatively short skip, Sporadic E. He was using a horizontal beam and a vertical dipole to do this, and from your school physics you'll remember Lissajous figures. So he's feeding one audio channel with phase coherence into one axis of the oscilloscope, effectively, software oscilloscope, and the other antenna into the other one. And you can see that the polarization, if you believe that actually represents a polarization ellipse, it's rotating, it's going in and out. Sometimes it's linear, occasionally it's circular, most of the time it's somewhere in between. But that's on a particular path using a particular setup, and I just wanted to sort of take that further and make it more systematic. So, you'll all have seen diagrams like this before. You'd be amazed how you go to a conference for electronic engineers or even HF people and industry people, and they don't necessarily understand this stuff. But what you have here are two views of the ionosphere, daytime, nighttime. As we know, the ionosphere is a region of, well, it's partially ionized plasma. It's mostly, up here at least, mostly it's gas atoms and molecules that have been ionized by EUV, extreme ultraviolet, coming from the sun. Down the bottom here, because the D region, all it does is absorb, but that's mainly X-rays down there. And this plot here, is the electron density caused by this ionization. So it's kicking electrons out of these atoms and molecules. And it's at these sort of inflection points where, just like when you stick a stick into a pond, it looks bent because the speed of light, the effective speed of light, changes at the boundary between the air and the water, it looks bent. reflection from, conventional HF propagation from mainly from the F2 layer, but also from the E layer, is actually bending. It's refraction. It's not reflection. Now, and just to give it some sort of scale, of course, the International Space Station is there, roughly. But there's enough atmosphere at that level to slow it down, and every so often they have to give it a boost to make it go back up again. So although it's extremely tenuous, there's actually enough there to have an effect on the ISS and also on our signals. Now, this is all very dependent upon the solar cycle. So as we know, as we heard this morning, we're at solar minimum, and there's less ionization up here than was, say, around 2000 or even 4 or 5 years ago. But there's one propagation phenomenon which is not dependent. Well, maybe there's more than one. Tropo obviously isn't dependent on the solar cycle, nor is meteor scatter. But sporadic E is an intermittent. It's called sporadic for a reason. It's an intermittent phenomenon that happens at about the same height as the E layer, but it's formed by a different mechanism. And the best theory for that is that rather than the ionization of gas molecules, which is the case up here, and also for the background, I like to call it E layer, this is ionization of, sometimes they call it meteor dust, meteor smoke. It's metal ions. And metal ions have got a couple of properties. Firstly, when you kick an electron off a gas molecule up here, it recombines pretty damn quick, either with the same atom stroke molecule or somewhere else. The metal ions have a much longer lifetime, so they don't disappear so quickly. Secondly, they're quite massive, and so they're very subject to, if you like, conventional weather, the wind. And so you've got a mechanism here that, again, this is the best available theory. You get a phenomenon called wind shear. Now, Jim will talk to you about what causes the wind shear. I'm not going to talk about that. But you've got a wind at one level going one way, a different level slightly higher up going the other way. And, you've the dynamo effect. You've got a Lorentz force, what is it? Motion field current. Because the whole thing about this is that it's in the presence of the Earth's magnetic field. You can't forget that that's what's going on here. So the wind's blowing it that way, the magnetic field's going that way, so the ionized particles go down. And if the wind's going the opposite way, they go up. So they get pressed together. Obviously, if the wind's the other way up, it blows it apart. So that produces an extremely thin but extremely dense layer of ionization, because the metal ions drag simply because nature prefers to have a neutral state electrically, drags the electrons with it, because the electrons are hardly affected by the wind at all because they're extremely light and extremely small. But they drag the electrons with it. So you get a very, very dense but relatively thin, very, very thin by comparison, layer, and it has can reflect a much higher frequency than the background ionosphere. Wonderful. All with me so far? Great. It's not particularly well understood, sporadic E, and there's a couple of reasons for that. Firstly, it's actually very difficult to predict, and it's difficult to model. And in fact, this morning, I don't know if you were in the HF propagation lecture first thing this morning, but Gwyn hates sporadic E. Jim manfully stood up and said, no. But and the reason is that none of the propagation models actually cope with sporadic E. If it's included in anything at all, and there is a simple model of sporadic E in one of the ray tracing programs that we've used, it treats it as if it's just a reflecting layer, a metal, like I said, a metal mirror, like it's a mirror. And it probably isn't. We don't really know, but it probably isn't. The other thing, of course, is that this used to be quite important commercially because of television. VHF television, but nowadays there is very little VHF television, so there's a lot less attention on sporadic E. But sporadic E will reflect 6-meter signals every year in the summer, peaks in late morning or early evening. You can rely on it. What you can't rely on is whether it's going to happen today or tomorrow, or whether it's going to happen in that direction over there. And it can happen at any time of day or night as well. So it's different, but the laws of physics still apply, if you see what I mean. So the question is, what is actually going on there? And that was, initially I thought, well, maybe even if the mechanism, and it's called magnetoionic double refraction, or birefringence, well-established theory for how waves get bent in the background ionosphere. We'll talk a little bit more about that in a minute. Is it that, but just happening in an extremely concentrated layer over an extremely short, relatively short distance, or is it something else? Initially, I was just interested. What I didn't realise was that actually there's very little in the academic literature about this as well. There are a couple of relevant studies, but not much. So there's that diagram again. I do like it. As I said before, the thing to remember is that this is embedded in the Earth's magnetic field. The plasma is embedded in the Earth's magnetic field. It's not very strong, but it's enough. And a linearly polarized wave cannot propagate in a magnetized plasma. That was a big revelation to me, actually. And simplistically, I sort of think of it as, well, the electrons are constrained to go round the lines of force, the magnetic lines of force. That's the only direction they can move. Again, Lorentz force, forcing them round, simplistically. So, again, this is pretty well established at HF, very well established. And it splits into an ordinary and an extraordinary circularly polarized or elliptically polarized components. And they rotate in the opposite directions from each other. And then it comes back to Earth, and you get whatever those two things add up to when it exits from the ionosphere at the other side. Now, a special case of that is Faraday rotation, which the EME people would talk to you about, or the satellite people would talk to you about. And if the ordinary and extraordinary ray travel over pretty much the same path, those two elliptical stroke circularly polarized waves will actually add up to another linearly polarized signal, if you assuming you transmitted a linear one, but it would be at a different angle, and that's Faraday rotation. But that's a special case of the more general situation where these two components, one going that way, one going that way, actually can follow significantly different paths, particularly at lower frequencies, but it also happens at 6 meters, and I've got a little example of what might be, but how that might be happening later on. So this is all the sort of necessary background, if you like, as to why this is, A, why I'm interested in it, and B, actually why academics might be interested in it as well. So there's a sort of a summary of why the polarization of signals reflected from sporadic E, or indeed the other properties of signals reflected from sporadic E. For instance, we know that sporadic E signals, you can, having been listening to them for 35 years, you can tell it's sporadic E because of the way it varies. It's subject to rapid fading. And a large component of that is because it's being bounced off lumps of ionization that are blowing around and moving all the time. And the question is whether there's an additional component of that which is actually due to this polarization rotation, the kind of thing that Graham TCT was observing on a number of signals about 6 or 7 years ago. So background ionosphere or rather sporadic E is formed by a different mechanism. It tends to be much more localized. In blobs, it could be tiny blobs, or big blobs. It could be small and intense and reflect 2 meters. It could be wide, hundreds of kilometers wide and reflect 6 meters or 10 meters. Don't let anybody tell you that you can't use sporadic E profitably on HF, by the way, because you definitely can. It's much thinner. You saw those although that diagram before had sort of layers, but it's not really discrete like that. It's a broad range with a varying density and a varying refractive index, and therefore bends the signals. It's much more rapid in terms of distance. It changes more rapidly, the refractive index. The electron density, I love my technical term there, it's very lumpy. We know that background ionosphere propagation, HF, is by this thing called magnetoionic double refraction, which is what I just talked to you about with the extraordinary ordinary rays. Probably that's happening in sporadic E as well, but even then, because of the nature of the size of the blobs, the thickness of the ionization, the rate of change of the refractive index, it may well qualitatively or quantitatively come out with something different. And the path length within the layer, which is definitely quite long for typical HF propagation, could be quite relatively short, which might explain why sporadic E signals can be extremely strong. Extremely strong. It's almost like a free space sometimes. So my experiment, I can talk about the technology, if you wish, but essentially I limit myself to signals between 1,000 and maybe 2,000 kilometers range, because I don't want to be confusing multi-hop with single hop. I don't want to be confusing sporadic E with tropo, and I don't want to be so high, the takeoff angle to be so high that differences in ground gain between horizontal and vertical screw up my measurements. Initially it was an ANAN 100, now it's an 8000. Nice, if you don't mind sort of having to tune it all the time. But it's got a feature built into it, which another colleague from Bath, or formerly from Bath, Ben P5B, brought me from his research, which is a way of capturing the IonQ data out of the software that runs the ANANs. This is HPSDR. But a facility that's built into HPSDR is it's effectively a chart recorder. Remember chart recorders, everybody? I can remember rolls of paper, pens, ink all over your fingers, all of that. It's got that sort of built in, which is what I was using for my initial work. And for an antenna, I use Innov antennas, which is a KSC LFA antennas. It's 10 meters long, by the way, 9.6, I think. 7 element, and it's 3 wavelengths, 18 meters or so above the ground. And although also, of course, that enables me to work DX on 6 meters, so you know, I wasn't exactly crippling myself by doing this, but it means that both antennas are located on the same boom. They're both well clear of interference from the ground, and they're both the same gain, and we hope the same properties. What you can't do if you've got a vertically polarized beam is have a metal stub mast. So that is actually fiberglass, and the cables have to come out of the back. Otherwise, again, they're in the plane of the antenna. That's the only sort of difficulties of doing that. So, this research that I've been doing. The first phase, which is what I presented in 2016 here, was fast measurements, and by fast I mean 15 samples a second, which was a lot faster than any previous measurement of polarization. There are only 2-3 published examples of people measuring polarization via sporadic E. I would find a beacon or another signal, point the aerial at it, and then see what happened to the relative strength of the two signals. Phase 2 was something slightly different, which I will explain, but I wanted to get a sort of a bulk view of what happens over a number of paths over a significant period of time, what happens on average, if you like. And with both of those, I was measuring just the 2 amplitudes and calculating a sort of a pseudo polarization angle that goes with that. Because to really understand the polarization ellipse, you actually need to know the phase difference between them as well. And then phase 3, which is still currently being worked on by me, But I've got some initial results from is even faster, 6,000 or 24,000 samples per second, but measuring the amplitude and the phase of those two signals using this facility that Ben got the HPSDR guys to develop. And then that is analysed that's analysed later. So in fact, I've spent most of this last year analysing 1 2-minute record. People build PhDs and scientific careers on 1 second of data, so I don't know why I can't do it on 2 minutes. Using a thing called MATLAB, which is a mathematical analysis package. So here's a good example, which some of you will have seen. So that the black is the horizontal signal on the horizontal antenna. This is a guy in Sardinia. He's on SSB, which is why there are gaps in it. The red is the signal on the vertical antenna. And even if there were differences in behavior of those two antennas, even if there were other effects that I'm not compensating for, it's changing. There's no question that it's changing. So that, and by the way, he was transmitting horizontal because I asked him. You know, he's a well-known DX or ISE or BSR portable. He was transmitting horizontal. So they were sort of roughly equal up here. Then the horizontally polarized signal virtually disappeared and then sort of crept back up. And you can imagine that the net polarization of all that is changing over this period of 3 minutes in this particular case. And if you then, and I was doing all this on spreadsheets at the time, spreadsheet king. If you then calculate based on those amplitudes, one of the great things about the ANAN and HPSDR actually measures signals in dBm, decibels relative to a microwatt. So you've really got something, sorry, milliwatt, microwatt, it's all about milliwatt. It's like having an electronic voltmeter attached to the aerial. You know, it's not subject to the vagaries to anything like the same extent of your average S meter, where an S point is whatever makes their radio look sensitive when people try it out. So if you then calculate an effective polarization angle, you can see what's happening to it. And not surprisingly, you know, they were roughly equal for a bit. There was a little spike, so 0 on this line, on here, on the left-hand, sorry, for those watching in black and white over there, it's the left-hand axis. 0 is horizontal, 90 is vertical, and you can see that the signal was sort of roughly somewhere in between. It went sharply horizontal for a very brief moment and then spent a long time vertical. And that's not unusual. There have been occasions when every signal coming from a particular direction, almost certainly being transmitted horizontal, was actually coming in vertical. So I hope just from looking at that you can see that polarization change, rotation, can be a major factor causing fading on 6-meter signals. Not all the time, but certainly some of the time. Here's another one. That's a beacon, HD7BVA, over 200 seconds, so 3 minutes and a bit. And again, you can see, so this is just the polarization bit, by the way, rather than the, so this is this calculated pseudo polarization that I was talking about. And you can see that it's sort of cycling up and down. And if you look at, this is a different recording, but if you look at it blown up, so this is over 20 seconds, you can see it's not varying in a random, completely random way. Something more subtle than that is going on. I should say the only signals that you'll come across that are actually randomly polarized are from hot things and from the sun. But you can, you know, there's a continuous sort of over seconds to minutes, depending on the direction you're beaming in, the day of the month, whether there's an hour in a month, whatever it is. And it's changing all the time. So this is I0JX beacon, although I gather he's now taken it off the air, unfortunately. But again, is that up there? Is it down there? Whatever it is, it's moving, it's changing. So we need to worry about it. It also happens on multi-hop. That's from D4C beacon. Pattern's not so easy to see, and there's probably 2 reflections in this, so that's maybe not surprising, but nonetheless, you know, there's quite a range of net pseudo polarizations there. And similarly, 3-hop probably, might be 4, from Ohio, from WZ8D. Now, he was actually, unlike most beacons with low power and an omnidirectional area or something, he was actually transmitting on his beam. I emailed him afterwards, and he was just running his beam, pointing at Europe. But again, you know, you've got that range, and it's sort of moving in a sort of somewhat coherent way. So it happens a lot. You know, first conclusion, if you like. So that raises some questions. What does that tell us about what's going on in the ionosphere? It's from a radio amateur point of view, is there a way I can improve my reception by compensating for that in some way? And I don't know yet, but I've got some thoughts on it. So that was one set of things. Everybody happy so far? Yeah. So that was phase 1. Phase 2, which was stuff I did in 2017. How long have I got? 5. Whew. Okay. I've obviously talked too much on this first bit. So this is using FT8 as the monitor, looking over a long period, and there's a clear distribution. It was alleged, you know, there's nothing over here, nothing over there, because if a signal is strongly vertical, there won't be much in the way of horizontal and vice versa. And if you haven't got 2 signals, you haven't got a measurement. But I've actually tried artificially raising the noise level, and in fact, this shape is maintained, so it's not an impact of the fact that you've got a... But whatever it is, at roughly 45-ish degrees, and that is consistent with, as are all the others, with elliptical polarization that's rotating. So at the end of phase 1 and 2, and this is the bit that's been published so far, and I can give you, email me afterwards if you want a copy of that paper. Sporadic E signals frequently have a strong net polarization. It happens multi-hop, single-hop, averaged over long periods. As you sort of expect that. If it's doing that all the time, then on average, the 2 amplitudes are going to be roughly equal. But is it caused by a linearly polarized or elliptically polarized signal? Is it right hand or left hand? And hence, maybe, is it the O or the X, the ordinary or extraordinary ray? And is it, therefore, this magnetoionic double refraction or not? I'm going to skip over the next few. Come on, go. Ah, that's interesting. Why won't it move on? Right, so this is some stuff that Ben P5B gave me from his research, which is into NVIS, and it's commonly believed that for NVIS you need your aerial as low as possible, provided you can resonate it. He actually did some properly controlled, carefully controlled measurements and proved that it wasn't, and the optimum is somewhere between. So this is, if you like, this is the difference between amateur radio interest and what he calls experiential learning. I think he calls it experiential learning. Is that right? No. Experience-based opinion, as I knew it was something like that. And if you do it properly, carefully, consistently, then rather than, it's well-known fact that it's better. Like it's a bit like sporadic E is called by thunderstorms. It's one of those things that becomes part of the currency, but unless you look at it in a scientific way, you're barking up the wrong tree, possibly. So I'm now going to talk about phase 3, accelerating, showing that this is a bit of analysis that Ben did that shows that without the phase information, you don't know enough about the ellipse, that if the vertical signal is twice as big or 6 dB bigger than the horizontal signal, then the polarization ellipse could actually be any one of those. But it's not down here, it's not horizontal, it's vertical. So I compensate, this careful measurement, you have to think about what are all the things that could screw this measurement up, if you like. So there's a whole list of the things that I've measured, compensated for. Those first 3 actually get measured for every single recording that I do. These ones, the antenna cable, electrical length, and so on and so forth, are things that are done on a one-off basis. But I've tried to design out. Now, so this is that signal that I've been looking at for the last 9 months. And it's one record of the Hungarian beacon over a couple of minutes last August. So on this top chart, the red is the vertical, the blue is the horizontal. The ratio of the horizontal to the vertical is reasonably steady all the way through this. I've realized after working on this for quite a while that this is actually not a typical situation, actually. But it's a very interesting one. But the phase difference between the H and the V is not 0, so it's not linearly polarized. It's not 90, so it's not circular. It's roughly 45, close to 45. And the question is, what causes that? Is this, if you like, a native mode of elliptical polarization that is being propagated, or is it the sum of a left-hand and a right-hand signal? It would be very surprising if those left and right-hand signals were actually in phase with each other for that long to make something as stable as that. So let's say this is not for publication. What I did do, though, is a nice little routine in MATLAB that allows you to draw the polarization ellipse. And this is one sample pictures of what the polarization instantaneously looked like in 1 second intervals. So 49, 32, 33, 34, 35. And you can see there's fairly consistent pattern. The ratio of the long axis of the ellipse to the short axis of the ellipse is called the actual ratio. If it's circular, it's 1. If it's linearly polarized, it's actually infinite because the width is 0. But that is the official definition. So that's the same amplitude plot, and you can see that the axial ratio was pretty constant. The angle was pretty constant, as you could see from those pictures, over quite a long period, and the axial ratio was like 2 and 3, and again, very constant. Right, John, I can see you hovering there. I don't blame you. I got too carried away with the first part. So in case you think, I've spent ages working on this one, I'm pretty sure about this one, that's a typical situation. Here's another one. The scale on this is completely different. Blue is still horizontal, red is still vertical. The ratio of the horizontal to vertical is now going from minus 30 dBs here to plus 20 over here. The angle, the phase difference between them, this is on a signal north-south to Spain, is going from minus 180 to plus 180. This wraps round, so it's folding back. And if you look at the shape of the ellipse, it's changing constantly. It actually looks as though it's rotating there. And on this chart, if it's blue, it's right-hand circular. If it's red, it's left-hand. So it's flopping from right to left all the way through, whereas that other recording was much more constant than that. So whatever's going on, whatever understanding we develop, has to be able to cope with both of those extremes. This is the sort of extreme. I deliberately picked one that was extreme, but it happens. And it's flipping right to left over a very wide range. So can I do one more thing? Here's an interesting thought. Very simple ray tracing model. The red is the ordinary ray, the extraordinary ray. The blue is the ordinary ray. And this model, very simple, has a uniform layer of sporadic E right here. You can see that because the refractive index is, the response to the ionization is different between the two ways, you've got a completely different path. So that here, the extraordinary ray is being reflected, whereas the ordinary ray is going straight through. And that offers the possibility that maybe you could actually extend your range when an opening's beginning by pumping into the extraordinary rays preferentially. And I'll stop now, John, because I can see you over in there. There's just so much to talk about.
Hello? Sorry. Very sadly, I could sit through this for hours, but then I'd want to demand to be asked to his Viber for his PhD at the end. So first, let's have a hand for Chris for giving a really interesting talk. Secondly, the observations of a veteran from much higher in frequency is actually the amount of Faraday rotation you get depends on the path length in the ionosphere. And the problem is that the longer and longer the path length that you get in the ionosphere, the more sporadic E you get, the more you tend towards elliptical polarization. And you didn't...
You mean even for moon bounce?
Even for moon bounce.
Yeah.
And the difference between east-west paths and north-south paths is compounded by the angle of the Earth's magnetic field that makes it even worse. And I don't even need an answer. I will take one question from the floor.
Okay, this is an academic, so I think we can be sure it's going to be a tricky one. Hello, Gary.
No, not. It's not. The phase one.
Yeah.
You had cases going from 1,500 to 6,000 kilometers.
I did.
And I seem to see the oscillations. You didn't blow them up, but were they typically still just a few seconds oscillations?
Yeah, you can actually, from those charts I did show that it's more complex simply, I guess, because you've got multiple reflections doing different things.
But it's still
but
very,
there's still
very short.
something,
Yeah.
you know, but there's not a single period. I'm not saying it's always at X
Right.
seconds. It's
Yeah.
anything
Well, and you
between-
had commented that it was sometimes maybe up to a minute or two.
Yeah.
So,
Yeah.
so it varies from maybe seconds to minutes.
Correct. And
that's
that first
amazing.
sample, that first graph I put up was minutes.
Yeah.
It
Yeah.
was
Yeah.
like that.
It's amazing. It's really, really good, Chris. Amazing work. Thank you.
No, it's really fantastic work, but I'd argue with his first thing that traditional amateur and professional speak thinks that sporadic E is almost specular. In other words, it's over a short distance. Experience is now showing with big ERP and multiple polarization at higher frequencies that actually a single hop can be 3,000 kilometers, where it has to be caudal in its nature as opposed to specular in reflection. So I've had my little two-penny worth. Look, thank you very much, everybody. Thank you, Chris, for a splendid presentation. We hope to be all along for your Viber. And good luck with the PhD. So let's have it again. Chris for IFX, thank you. It's time, so please come back. Marcus Walden will be talking about tropospheric propagation and some of the latest